Okay, so our first speaker today is Robert Kosara. He must feel at home here because he received his PhD here and also spent his first years as a postdoc in Vienna. But he's now a professor at UNC Charlotte, though right now he's a researcher at Tableau software to get a feeling for industry. And his research has largely focused on the theoretical foundations of visualization, but today he will talk about the validity of a visual representation of data and the presence of uncertainty in this data. So,
thank you. Instead of taking folks' advice here and actually plugging before my talk, sorry about that. Good. So what I want to talk about is basically the theoretical side to what Paul just talked about, which is why do we want to figure out what uncertainty is, how to measure it, and how to manage it, and then how do we get there on this kind of bigger picture level. And this might also work as a bit of an introduction or kind of an overview to start off the other points. So I wanted to start with a little quote by one of my big heroes, Donald Rumsfeld, who made this statement a while ago in the lead up to the war in Iraq, where he said, "There are known unknowns, there are things we know we know. We also know that there are known unknowns. That's to say, we know there are things that we don't know. But there are also unknown unknowns. There are things we do not know we do not know." And this was ridiculed at the time, and the statement, and of course this whole political side, which I won't go into, but the statement itself is sound. There is a lot of things we don't know in visualization, and we don't know that we don't know. So my point that I'm trying to get to, and I hope to show you some examples, is that there are too many unknown unknowns in visualization. And I hope that by the end of this talk, there will be a few more known unknowns at least, and we will be able to move those towards the known knowns, perhaps, or the whatever, unknown knowns or something like that. But anyway, so the point here is that there are too many things we just don't know about visualization. So I'm just going to show you an example. This is a visualization that we did, this is a Richard Scoop's work and my work on privacy preserving visualization. We just took a regular sanitization algorithm, ran it on some data, and visualized the results. And this is what comes out. And I'm going to show you a different example of this. This is what this looks like. This is a different algorithm we developed. Which one's better? This one? No. Go back. Or this one? Right? It's not that hard to figure out. I mean, I hope it's pretty clear. But why? Can you give me an objective measure that tells me that one is better? And if I claim that this is pretty good, so you will probably agree with me that this is not good and this is better. Okay, so we have a relative measure here. Totally unscientific. Okay, but is this good enough? Is this actually useful? Would somebody actually be able to use this in actual work? I don't know. I think it's possible, but I can't prove it. And so the question is, how do we do that? How do we figure that out? And on a much more kind of bigger level is, how do we know what changes we make, what impact they actually have? And this is something we just can't do right now. We don't know it. And this goes to much simpler examples even. So let's look at a bar chart and ask a simple question. If I have a value, if I'm showing values, so let's say sales or whatever, income, whatever, for a company, millions of dollars or euros or whatever, if my value changes from 65 million to 67 million, will I be able to see that in my bar chart? You can't answer that question. You have to know a few things. You have to know the scaling, you have to know the resolution, you probably have to know the zero value, because you could cut off the axis at some other value than zero, and then maybe you can answer the question. But how many programs can do that today? I don't know any that do that. And or the other way around, or well, actually, so what if the change is 65.3 to 65.7? I mean, it's the same question, it's just different numbers. So if I'm interested in number in differences, if I want to see things, how do I know that the visualization is actually going to show me that? I just don't know that at the moment. And the program can tell me if my current settings allow me to see what I want to see. And then the other way around, if I want to know how much change does one pixel represent, I have no way of finding that out. Okay, I can make the chart bigger, but that's all I can do. This is as scientific as it gets today. And that's just a really bad situation. And then, of course, it gets a bit more complicated when we get, so figuring this out is some fairly basic math. It's difficult, but I don't know a lot of people who have done this. And then it gets more complicated when you get to angles and things like pie charts or parallel coordinates, where you have these angular things and then there's overplotting and all kinds of stuff. And the Rita and I have done some work on this. Or a star glyph, where you again have angles, and depending on where something is, on which angle, on which part of the star, the resolution is different and stuff like that. So things really get more and more complicated. And of course, this is all thinking from the InfoVis point of view. In Cybis, it's much hairier, but also kind of much more interesting because there's a lot more stuff going on. But there's even less, at least less work that I know, that's really looking into that to measure these things. And so what I'm trying to propose here is an extension of the usual visualization pipeline. But this is basically the first steps, and we're not going to argue about individual steps here, which one has to be there, which one doesn't have to be there. But in principle, there are a couple of steps, like data mapping and visual mapping, and then we get some kind of display. And that's kind of just the typical way of doing things, and it's all forward. So it goes from one thing to the next thing to the next thing. In the end, we get some kind of display. And first of all, I argue that we need to include the other side of the equation, which is the human, and actually figure out how we see things, how we perceive things. So once we jump over the display gap, or the air gap between the display and the eyes and the human brain, we need to see what's going on there on the perception and the cognition levels. And there is a kind of feedback loop here that goes from somewhere here back to here. And that feedback loop is, I can switch to a different visualization. If I don't like what I'm seeing, if it's all cluttered up, if it's all just useless, I can change my values. But very often this is based on just guessing. I can see, or I can't see something, let's try something else. I can't see the color differences, let's try a different color scale, for example. But what these things do is something that's kind of just trial and error. And that's really a bad situation. But in addition to that, I think we need something that's actually much simpler than that, which is to add some feedback here on a purely computational level, where the systems that we build understand what their output is. This is what's called a closed loop system, or a feedback loop that goes from the output of whatever you're doing back to the inputs, and then it adjusts the outputs based by twiddling the inputs, or twiddling with some kind of knobs in the inputs. And this is the way engineering works. Almost anything you use today has these feedback loops in it. Any power plug that you use, or power converter, is going to have a feedback system that measures the output current, especially the output voltage, and it's going to adjust the values or adjust some settings in the system to keep that at the right level, because nobody would build a system in engineering today that looks like this. It's an open loop. It's a disaster waiting to happen. It's not going to work. It's going to blow up at some point, because it's just not going to be able to respond to changes, and that is extremely important. So we need to understand what's happening in that loop, in that pipeline, and to do that we have to build a loop where that part here knows, that the system knows what's happening here. And that doesn't have to be of course, the real kind of holy grail would be to do that, to measure these things somewhere over here. But as we just heard, that's not exactly possible, at least setting up for the moment. Or maybe we'll hear some more about that a little later. But I think right now we would be doing really well if we had a really good system that starts here, that knows something about the output. Some of this is image processing, but it doesn't have to be. A lot of this can be done on a purely theoretical level by knowing how, or on a purely mathematical level, I should say, by knowing how things transform from the data through the different stages onto the screen. And of course, by knowing what we actually want. And we've done some work, so we being different students of mine and I, this is a paper we wrote for a Springer book a while ago, Caroline Sienkiewicz and I, and Aritra and I have done some work on prognostics. There's other work, this is parallel coordinates diagnostics. This was based on the idea of scagnostics, which is similar work on scatter plots that was done before by Anand and Wilkinson. And there are a number of papers that people have, and Heike's work and Vincent's work, that have worked on these kind of things, figuring out or looking at how the mappings work and what kind of information we lose along the way, which in many cases is fine. There's nothing wrong with losing information or losing some parts of the data, but we have to know what parts. We have to know if we're doing this for the right purpose. And we actually have a paper here at EuroViz in the first afternoon session tomorrow that Rich is going to present on a taxonomy of uncertainty causes in parallel coordinates. So that will be about this kind of topic as well. So there's a little add here about for that. And apparently I'm talking much faster than I was planning to, so this is my final slide, but that gives us some time to argue, so I hope that there will be some discussion, and I'm happy to answer any questions that you have.
Okay, so are there any questions? Yep.
For you.
Yeah, thanks for the talk. And I was wondering, I mean, this goes also in the direction that we have the first loop, but also the second loop. So, do you have any idea how to attract like people which deal with the broader, the wider loop?
Sure. Yeah. There's actually quite a bit of interest. So I had a discussion with somebody in cognitive psychology a few months ago, who had some interesting things to say about this field. He felt that psychologists are very so this is somebody else's words. Okay, I'm not talking about anybody in the room, but he said that the psychology is very inbred. That a lot of the work that's being done is kind of redoing similar things and kind of thinking about each other's work, but not really looking outwards. And so there is a certain, so some of the more progressive younger people, I think, are interested in figuring out what can cognitive psychology, what can perceptual psychology do for other fields. So we in visualization, we don't necessarily have to do all this work ourselves, but we should partner with folks in those areas and find the ones who are interested in that kind of work. And I think there's a lot of work actually that has been done already that can be adapted, or that can be the basis for working on those kinds of issues. And there's definitely interest, I think, in that. So I think if we can just get some folks from those areas here, or we can just talk them into projects and potentially funding, because I think this is, of course, cross-disciplinary work that should be fundable. That would be the way to do that.
Yeah, and the thing is actually what you say is like funding, and I already talked to many, or to some psychologists, and for them what we are needing is basically trivial, right? And yeah, but sometimes it's from their side it's somehow like, oh yeah, we understood this, and why don't you see this, and where's the problem, right?
You're talking to the wrong people.
Yeah. Okay.
I don't think that this is trivial at all. No.
No, I also don't think that it's trivial, but it's very complicated to tell them in which direction it is non-trivial, right? Because from the fundamentals, so besides this, they basically like have already left this field somehow behind, or left parts of the field behind. So
I could give you a list of things that nobody can explain today, and where there would be a lot of good work to be done. So there's definitely a lot of potential for work. So if we're talking about basics, like, can we perceive line lengths more easily than angle? That's all done. But even though I'm not entirely actually convinced that that's really true, but that's hard to sell today. But if you're looking at things like, we've done some work on metaphors in visualization, and there is no explanation why certain things happen in visualization that we've seen. And there are other things about the weight of colors. Different colors have different perceived weights. How do those play a role in visualization? And that's actually, I should have put this on my slide there as well. So if you talk about pie charts versus bar charts, whatever, that's relatively easy. If you talk about color perception, that's a whole can of worms. And I don't know anybody who has a grasp on that. That's really strong enough to say, well, I can now write an algorithm that can fix my colors. It can predict how badly my colors will distort what I'm seeing. So I don't think we're anywhere near that. And that's just a simple little problem, and there are lots of others. So there's tons of work to be done that should be, again, talking to the right people and I don't know, making the connection, but with the right people. But I'm sure there's a ton of work that can be done, but there should be a lot of interest from that side.
Okay.
Hello, Hendrik from University of Constance, and I claim to be a bit illusionless. I don't know how to say it. So for the feedback loop, I mean, I understand your example from the power plug. Yeah, you have clear goal function, convert 220 volts to 5 volts, and observe it and try to be in this direction. I can understand it for color mapping. Yeah, you can put something on your monitor and that you get the color out of this machine which you want to have. But especially for information visualization, can you give an example which is more concrete, specific?
Yeah, that's the kind of thing. If you're looking at data, and you're quite, this is actually a very common question. When you talk to people who are using visualization as a tool and who don't care about actually what's happening in visualization, they just want it as a tool. And since I'm working at Tableau right now, this is something that we actually get quite a bit. If I do something in some kind of dashboard, in some kind of visualization, and I have my data changes, do I actually see particular changes that I want to see? And that's why people do things like they cut off the y-axis. Because if they include 0, then the changes are very small. But they want to see the changes, they're really important because their values, they don't change that much. But the changes are important. So if you just, if you take away 90% of your scale, then you can see a lot more of a change. Now this change is much bigger, but of course it also looks much bigger than well, much bigger than it actually is. So my question could be, I want to see change, is this going to show me that? And what other ways could there be? So I think my point here is, you provide that goal function. So if your question or your goal is, I have 25 categorical values, how do I represent them so I can actually tell them apart? Then that's a goal function. Or if I have a lot of values, a lot of continuous values, and I want to see changes down to 1%, how do I do that given my current display setup? That kind of thing. If I need to show a part-whole relationship with 12 pieces of the whole, is it going to be possible, what kind of chart can I use for that? What kind of visualization can I use for that? Pie charts are going to be problematic depending on, the sizes of those slices. And so there's a lot of things that you could, that play into this that are much more complicated, obviously, than the goal function of provide a particular voltage. But that's what makes this non-trivial, because that even knowing what that is going to be hard, of course. But I think there's there are a lot of kind of common things that people would want, and those could be kind of things that you could just kind of check off and say, I want this, I want that, and then you have your selections. But the point again is that I think the deeper question is that even if I wanted to ask this question right now, I just can't, because there is no mechanism for doing that. And so that's really what I was trying to get to. Of course, then there's kind of the technical question of how they actually provide those. But that's really, once we have some kind of system that can actually measure those things, then we can kind of take that next step and figure out how we actually specify that.
Oh, I'm sorry.
I think you
go ahead.
Thorsten from of IG. If you refine the inner loop, the automatic loop, more and more, do you think you ever run into a stage where we can replace human visual perception by just telling them what they actually see in the picture?
No. No, because we would. There's this quote in the Hitchhiker's Guide to the Galaxy where the philosophers are protesting against building the computer, whatever the thing was, because they demanded certain well-defined areas of doubt and uncertainty. And I think that's actually one of the good things about psychology, is that we have these fairly well-defined areas of doubt and uncertainty that we're never going to get to, at least not in our lifetimes, to actually figure out, which I think is actually a good thing, because we need a certain amount of mystique, otherwise it's just, if it's really all trivial in the end, it would be boring. So I don't think we're going to get there anytime soon. And of course we will also defeat the purpose, because we don't know everything about what people want to do with those things, and we would kill any kind of discovery that happens that you weren't looking for. So yeah, no, that's a clear answer to that.
So one more question?
Yes. Wolfgang Vienna University of Technology. Thanks for your thoughts. It's interesting to look at it this way. I would like to question, especially this picture you have here of the reference model. What I didn't really get is why you have to have this feedback loop after the visual display. Because then you only have your pixels on the screen, you have
No,
lost a
that's
lot
not-
of
right.
information. If you do it like on the visual mapping, you already know, okay, if I have this and that change of data, it will be
Right.
less than a pixel, so I adjust here already. So
Right.
why do we need to have it there?
Right. So that's what I was trying to say is that some of that could be based on image processing, which obviously would happen after it's rendered, but this is conceptually at the end. So the idea is not that it's measured at that point, but that you want to know you want to measure what happens there. So it has to be based on the properties of your display. So you would have to know things like resolution, like screen size, and things like that. Bit depth of your color display, maybe the gamma, whatever. So you would have to know a lot more about the display than just knowing how many pixels or how many lines you draw, things like that. So you want to essentially predict what's going to happen on the screen, not necessarily rendering. Yeah, I agree with that. But the point is, you don't want to measure just stuff that's happening within the visual mapping. You want to know what the whole pipeline is doing in the end, and then be able to adjust it.
Okay, so I think we should continue at this point. We have later in the coffee break, we have time to ask other questions. Yes, thanks to the speaker again.